Yes, sir.
Okay, cool. So so just a quick recap about the previous class. So we started off looking at some concepts in machine learning, and we talked about classification, regression, ranking problems. Okay, and one point I want to make here is about the ranking problem. There was a question about whether we can consider ranking as a regression task because you're trying to order various objects, and that's what you're trying to learn, a function which orders various objects. So then can we not think of it as there is an underlying score function which, and you take the ordering of the scores to get the ordering of the objects themselves. Okay, so yeah, sure, this is something which of course conceptually it makes sense, you could do that. But one thing to just keep in the back of your mind when you think of learning these kind of functions is that there is a dependence on what kind of data is available to you. Okay, so sure, if you have some kind of metric which is available at your disposal, features, and instead of the class label or instead of the ranking itself, if you additionally also have a score function from your data set, this is definitely something that you can do. You can consider it as a regression problem and just learn the score functions if they directly map to the ranking. But many times what happens is the score function is not really available to you. Okay, it's not there, it's not part of the data set, or it's not like a very obvious part of the data set. So you have to do some extra work to design some score function which you can actually get from the data. Or another option is to treat it as a classification problem. So one possibility is people either look at the rank itself as a class. So there's some more constraints that you'll have, that there can be at max one object of a particular class. Things like that will come up in your function that you're trying to learn. Or many times what people do is you try to do a pairwise classification. You see whether for a given query or whatever you're trying to look for, you look at whether one object is more it's higher ranked than object 2. Okay, and you try to learn a classifier which tells you this, and you try to learn pairwise classifier for all instances. So this is expensive, and people try to use this idea to propose more enhancements or improvements. Okay, so just something I wanted to tell you about ranking, because I mean, typically we think that a lot of things are conceptually okay, but there is also this dependence on the underlying data, because that's what you're trying to use to learn. Okay, the training set, or the training set actually. So that should have what you're looking for. Okay, so yeah, then we talked of hypotheses, so or models that you come up with. So these are actually underlying assumptions on your function that you want to learn. So essentially all of machine learning is function learning. You're trying to learn some function of this form. Okay, and the question is now, what kind of assumptions do you make? You cannot learn an arbitrary function. You need to have some structure to the function. Okay, so that's why there are a lot of machine learning models. And so what we winded up with in the last class was we were looking at the perceptron algorithm, and what we did was some recap on concepts in like geometrical concepts involving vectors, hyperplanes, okay, and inner products and so on. Okay, so with these backgrounds, I think now we are ready to get into the perceptron, the model, and the algorithm. Okay, so recall that a hyperplane was something like a generalization of a line. Okay, and the general equation of a hyperplane was this. Right, so W transpose X equal to 0, or in general, you can think of it as W transpose X equal to some B. That's the equation of a hyperplane. So what we will typically, you will see this in textbooks also, we will consider all of these Wx as column vectors. So there was a mistake in what I wrote last time. So this, you can write it as W1 to WD. This is a column vector. So transpose of this times X1 to XD. Okay, so this is equal to 0, and that's how you get this kind of an equation. So W transpose X equal to 0, or more generally W transpose X equal to some B. Okay. So that's the equation of a hyperplane. And then, we saw about what these half spaces are. And finally, what we said is, the underlying model, the model for perceptron is like this. Okay, so there are, your data has these two parts. There are these features and there are these labels. Okay, so labels or classes. And so there are two classes. So it's a binary classification problem. And we have y's are either +1 or -1. Okay, and the way the perceptron thinks of your data is, there is a hyperplane. Okay, and if it is on one side, it's one class. If it's on the other side, it's the other class. Okay, so more specifically, there is a W vector, and if W transpose X is greater than or equal to 0 for some X, for a given X, if you have this W transpose X is greater than 0, it thinks of it as a positive class. Y is then positive, Y is +1. And while if it's on the other side of this hyperplane, so W transpose X is less than 0, in that case, it considers it as a negative class. Y is -1. Okay, so this is the case where, your W passes through the origin, right? But more generally, this, if you didn't want this 0, you could also have something like this: W transpose X plus B greater than or equal to 0. Okay, and W transpose X plus B less than 0. Right, so this is a more general version. So the same thing, so Y is +1 or Y is -1 if W transpose X plus B is less than 0. So that would just mean that, the hyperplane is something like this. It's on, it's not passing through the origin. Or another way to look at this is, you construct a new, you add a new element to your feature. For example, your feature was just X. Now, what you can do is you can just think of an augmented feature, so something like this, where you have an additional component with just one. Okay, and now your new vector, your W, could just be the original W and B. Okay, so then what it would mean is just you're taking it into one more dimension. So if your original X was in RD, now X tilde is going to be in RD +1. And then what you're going to say is just W transpose X tilde greater than or equal to 0 means Y is +1. And W tilde transpose X tilde less than 0 means Y is -1. Okay. So what I'm trying to say is that, we can just focus on this form, the greater than or equal to 0, less than 0 form, because if you want to include any other threshold other than 0, it corresponds to having a plus B on this side. Okay, and that corresponds to a new hyperplane in one dimension higher. Okay, so that's why we'll just focus on this assumption. Okay, this kind of a model for the perceptron. Okay, is this point clear? Are there any questions on this? Can you all just type in the chat box whether you understood this point? All right, that's good. So now the thing is, this is the model. So if you are given an X, now if you're given an X and if you had a W, now you know how to classify it. Now the question is, what is the correct W, right? How do you find what is the correct W to use? Okay. And how do you learn this? Okay, how do you learn W's? Okay. And so this is where we will need to use the training data. And so as we assume, like we have a training set like this with X's and the Y's. Okay, so maybe let me just call this Xi and Yi. Okay, so there are, I is 1 to some n. Okay, so there are n training instances. That's what this means. Okay, So what the perceptron algorithm itself does is a sort of iterative algorithm in order to learn the best W. Okay. So maybe I'll just write the algorithm first and then tell you why it makes sense. So the perceptron algorithm goes like this. As perceptron learning algorithm. So what you do is you initially start off with, you randomly initialize your W. Okay, so you randomly initialize your Ws. Okay. Now what you do is, so this is some W that you have, a W vector, and that gives you a hyperplane. And with this, you can also you can get an estimate for the Y's. Like given if you feed an Xi with this W, so if you get W transpose Xi, you'll get a value. And then if it is greater than 0, you will think it's the positive class. So that way you can use this W to classify with but this is a random initialization, so it might be a very lousy classifier. So what you do next is, you see if all the training examples are correctly classified. Okay, and you loop as long as there is a misclassified example. I'll tell you what that means. Loop as long as there exists uh, a misclassified instance. So what this means is that, there is some x. There's some x in your data set. There's some xy pair where actually y is +1. But when you tried to see W transpose x, you got a value which was less than 0. Okay, so remember this figure. So these were the positive classes. So all of them have, y is +1. And the W is like this. Okay, and the negative classes are of this form. I mean, they're ideally supposed to lie on the other side of the hyperplane. So assuming this is the hyperplane that you're looking for, the negative instances lie on the other side. And so for all of them, you have W transpose X is less than 0. And for all of these, you have W transpose X is greater than or equal to 0. Okay, so now what has happened is you randomly initialized W and you found one example which actually had the label +1. But because this was a bad W, you got that W transpose X was less than 0. So what happened was you got something like this. Okay, so this was a positive class. This was an instance which had y equal to +1, but it was lying on the other side. Okay, so now, so this is one possibility. So in that case, what you do, so if this is case one, okay, so that as long as there exists a misclassified instance, one case is like this. Then what you do is you have to update your W. Okay, so you have to change your W, right? Because this W doesn't work. So what you do is you just try to, you have to shift the W some way. And the update you make is like this: W is W plus X. Okay. So remember, W and X both have the same dimensions. They are vectors. So both W and X are in RD. So they're D-dimensional or D plus one dimensional, depending on whether you use a bias or not. So this term, this B term, this is called a bias. Okay, this is referred to as a bias in literature. So so generally you have something like this. W and X are both in the same dimension. And what you do is you just update W to W plus X. Okay. I will just tell you, why it makes sense, an interpretation for this in a minute. And there can be one more case. Now, for having a misclassified instance, the other case is there is an XY where now y is actually -1. But what you got was W transpose X is greater than or equal to 0. So something like this. You had a negative class somewhere here. Okay. So that is another case. So this is case 2. And this is case 1. Okay. So these are the two possibilities. Now in this case, what you do, if your misclassified instance was of this form, then what you do is you update your W to W is W minus X this time. Okay. And you keep doing this. Now again, so now you have a new W. And so now again, you come back here. Okay, and you see that you check all the instances in your data set D. As long as there is a misclassified instance in D, then if you found one, then it will again be in one of these two forms. Okay, and if everything was perfectly classified, then you just stop and you just return the W. Return the W that you obtained. Okay, so this is the formal algorithm. Now the main thing is, why does this kind of an update make sense, or this kind of an update? Why does it make sense? So let's just zoom in a little bit. So what we had was, there was this line W. So W was like this, and there was an instance, a positive instance on this side. Okay, so maybe something like this. Okay, and so this was the X that you had. Okay, so this was the instance X. Okay, this was the training point X, and here Y was actually +1. But what you got was, these make an obtuse angle here, and so W transpose X was less than 0. Okay. So now what are we doing when we do this W plus X, right? So what we are essentially getting is a new value of W, something like this, right? So we saw how to add vectors. So the new W would be like this. So this is W plus X. So this is actually W new. Okay. So this is what I refer to as W new. Okay. So this is the new W. Now when I see, so this is the new W, and the hyperplane is something which is like orthogonal to it. So let me just draw it in red, the new hyperplane. So the new hyperplane becomes something of this form. Okay, so basically it is orthogonal to this W new. Okay, so this is the new hyperplane. Okay, and so then there is some hope. So now here you see that this example is on the correct side now. Okay, so this is the motivation for doing this kind of an update. Okay, is this clear to you all, like why this update makes sense? Any questions on this update? It's just about adding vectors and seeing that it makes sense. Is it clear? Rishabh, you understood?
No, ma'am, I have doubt.
Yes, tell me, Rishabh.
Ma'am, suppose that if we take the data set in such a way that we do not have the clear separation between the positive points and negative points. Means in between the some positive point there is a some negative point, and in between the some negative point there is a some positive point. In that case, if you do this update like the W equal to W plus X or W equal to W minus X, should it not be W equal to W minus delta X or delta plus X?
So what is delta?
Means I'm saying that here X is a point, I think.
Yeah, so X is a vector.
Yes, ma'am.
Right?
Means vector of the training point.
Yes, yes, yes.
Ma'am, the training point can be to outlier or something. So on that basis, if we update, then W value will be maybe increase too much or decrease too much.
Yeah, yeah, exactly, Rishabh. So, yeah, that is a valid point indeed. So, in fact, one thing, I mean, I'll come to this point that there is, this algorithm doesn't work always. There are some cases it will not work. Okay, so first thing is that, the points themselves have to be separable. Okay, they have to be separable in the sense, the geometry of these points must be such that, there is a hyperplane which separates them, right? For example, if you had something like, some, let's take something like this. So, you have a lot of points here, okay, and maybe something like the example what Rishabh gave was like this: a negative instance somewhere here, right? So in this case, yeah, you cannot find a hyperplane which separates the data. So in that case, this algorithm is not going to give you, it's not going to converge basically, because you'll always try to keep making updates and you will fail, right? So that is true. So there has to be some assumptions on the data. So this learning algorithm makes the assumption that the input data, so the input data D has to be so the D or D train. So this is linearly separable. Okay, so there is this underlying assumption that is made in the data, and this is actually, some, like I said earlier, like what kind of assumptions you make about the data. That your model makes some assumptions like this. Okay, so it may not work always for some data sets which are not linearly separable. This is not going to help. Okay, so what linearly separable means that there exists a W such that all the positive instances are on one side for all x, such that y is uh, plus 1, and w transpose x is less than 0 for all x with y equal to minus 1. So as long as your data is linearly separable, you can do this update. Okay. um, Now, so Rishabh, so if your data is linearly separable, so that means there is a hyperplane. Somewhere there is a hyperplane which separates the data points. Then does this update make sense?
Yes, ma'am. I have only small doubt. Means x can be the outlier. Means value of the x may be too much, or means it can be high magnitude. So I think, but our weight it's not always to be too much high, na. So I think it's not optimal too much. Means what I want to say that it should be delta x or something, because suppose we have many points, means not the one vector.
Mm-hmm, mm-hmm, mm-hmm.
Ma'am, then is it working or not? Means because what we will do in each time, we will for each vector, means suppose we get some extra data point, means
Yes.
then I think every time our weight may be affected.
Yeah, yeah. So your the weight vector, this vector W is going to be sensitive to each and every point. Like sometimes you can have one point which kind of flips the whole W. Now what happens is, in one iteration you changed your W. Now in the next iteration you can have that, so with this W, there were a lot of points which were actually fine. But now you made this update and all of them got disturbed, right? So such things are bound to happen. That will definitely happen. Okay, but the hope is that because of this kind of a geometric meaning for these updates, this W, if you change it, you're like trying to flip it towards to make this, at least this example, work. So whatever was misclassified instance you found, now you're focusing fully on that and trying to make that work. In the next instance, you will try to focus on another one. You will try to keep doing this. Okay. And similarly, I mean, the same kind of motivation will hold even for this part, the W minus X part. You can try to work it out. But, one interesting thing about this algorithm is it seems like it's not optimal, right? Or it seems like, why should it work? Okay, but if as long as the data is linearly separable, as long as there is a W like this, there are like proofs which say that this kind of algorithm, it converges in finitely many operations, in finitely many iterations. Okay, so this is the perceptron convergence theorem. So we are not going to go into the proof of this theorem. So when you do machine learning in the next semester, you'll probably see the proof of convergence. But so that's a very surprising thing about this algorithm, right? In fact, even in a single step, right, when you make this update, the W is W plus X, do you expect that also to work, or do you expect that also may not work, or what do you think?
Ma'am, it may
It,
work.
it may work. Yeah, so this was a case where you saw that it worked, but there you can construct some examples where even for even for that point xy itself, which you wanted to tune it for that point, but even for that point an update like this may not work immediately. So maybe I can just try to show you an example of this. So maybe if your data was like this, so this was the W, and maybe your point was, let's say something like here, maybe yeah, somewhere like, okay, so let me take something like this. Okay, so this was the negative point, and so this was your X. Okay, now what could happen is, your the change to this W may be a very small number. So something like this, the W can become like, somewhere like this. And okay, so maybe in this case it works, but what I'm trying to say is, a very small update can happen here, and that may not change the hyperplane significantly. So something like if it's very close here, right? So maybe something like this. Let's see if that works. Um, right, so maybe somewhere here it comes, and then maybe it's still on the wrong side. Okay, it's close but still it's on the wrong side. So this kind of a situation can happen where, even for that point xy itself, you might not get that W. Now when you make this update, you might still not get it on the right side. Okay, so that's why it's a very surprising result, that it says that, the algorithm converges this loop. The number of times that you do this loop, that is only if it's a finite number. So it converges in finitely many iterations. Okay, finitely many iterations if the data is separable, if linearly separable. Okay. Um, okay, so this is the theorem which we are not going to prove this. Okay, but you'll see it in more detail later. So that's why, in some sense, this is like a very surprising algorithm. But there are some caveats here, like, your data has to be linearly separable. Only then this model makes sense. Okay, so Rishabh, I don't know if your questions got answered or not. Um, there are these issues are there with it, like, it is sensitive to one point and all that, but in spite of all this, the theoretical result is that it converges in finitely many iterations. Okay.
Yes, ma'am.
Okay, all right. Yeah, so maybe let me just pause. Are there any other questions, any other confusions? um, Aditya, does this make sense or anything bothering? It's okay. Aditya, you there? Aditya Jain. Okay, I guess he's not around. But can you all just type here whether it's clear, or, if there are any questions, can you just ask? It's clear. It's clear. Okay. Okay. So yeah. So in the beginning, I also mentioned that, most learning algorithms try to do something with the loss function. I mentioned this in the last class. So, what is the loss function? So, actually, what we can see is, it's kind of an iterative algorithm. It's trying to do something with the misclassified instances, maybe reduce the number of misclassified instances, or do something to adapt the misclassified instance. So, what is it that it's actually doing? Okay, so what's the loss function here? So it turns out that, there is an optimization problem. There is an underlying optimization problem that the perceptron algorithm is trying to solve, and it solves that optimization problem like perfectly. Okay, so the problem here, the loss function, is something like this. So the loss function is basically a function of your W. Okay, whatever you're going to learn finally. So it's measured with respect to that. So if, W is a good value, then the loss is low. Okay, and if W is a bad value, then the loss is very high. Okay, so in that way, that's how you construct the loss function. So the loss here, which I'll write as J of W. So this is actually, it's basically doing something like this. You look at all the instances where, yi, so this is the true label. So all the instances in your class, in your data set, where, yi w transpose x is less than 0. Okay, so what this means is, this will be less than 0 in one of two cases, right? So either yi is plus 1 and w transpose x less than 0, or yi is minus 1 and w transpose x greater than or equal to 0. So in either of these two cases, you're going to have that, this product yi times w transpose, this is xi. Okay, so xi. So let me write it this way, yi times w transpose xi less than 0. So basically these are the misclassified instances. And what it's trying to do is it's trying to take this value, w transpose xi. Okay, and actually yi w transpose xi, and it's taking the negative of this. Okay, and it's trying to minimize this. Okay, it's trying to minimize this quantity. Okay, so what you're trying to do ultimately is minimize jw, find the w which minimizes it. Okay, so that's the underlying optimization problem which is being solved. Now why this actually solves this problem, this is all something that you will see later. Again, the next semester I am hoping to offer a course on optimization. So most of these learning algorithms have an underlying optimization problem which and these algorithms are designed to solve that optimization problem. So actually you can show that it indeed solves this problem to optimality. Okay, so this is the loss function. Now if you change the loss function, this can be different. I mean, this algorithm may not work. Okay, so just an additional point about the perceptron algorithm. Now okay, so we made this assumption that the data is linearly separable. Now, there are some things you can do to adapt the perceptron algorithm, or to change this model to, I mean, to some extent. Okay, you cannot tweak it too much. But one thing that people do is, instead of x, so x is the features. So what you could possibly do is you could construct some other function, phi x. Okay, so so if x is in maybe rd, so x is in rd, so maybe phi x could be something in maybe something like rd2, so where d2 is greater than d. Okay, let me say d1 and d2. So this is something that is possible. So you using these features, you could construct some higher dimensional set of, I mean, a vector with in higher dimensions. For example, suppose x is something like this. So you have x1 to xd1, right? So this is the vector. Okay, so this is a column vector. And what I'm going to do, one possibility is I can take phi x as, I take all these x1, xd1. Then I also take the x1 squares, xd1 square. Okay, then I can take the products x1, x2, and so on, all the cross products. All these I can take and make a larger vector. So this is like in a higher dimension. So this has like more features. And now what you can do is you can try to, learn a hyperplane in this class, in this higher dimension. Okay, so maybe what you can do is you can take something like this. If w transpose phi x is greater than or equal to 0, you take y is plus 1. And so this is now W is also going to be in RD2. Okay, so you're going to learn, something a bit more complicated in that sense, hyperplane in a slightly higher dimension. So more parameters. Okay, so this is also something that people do, and it works for some kind of problems. For example, if you had your data set was like this, so your positive classes are like this, and maybe your negative classes are like something like this, all around this point. Okay, so then what you need, your decision, now you don't have a hyperplane which separates these classes, I mean these two classes, these two set of points. But what you can do is, you can have, if you're allowed to construct something like this, a circle, then you can have all the positive classes perfectly classified and negatives also perfectly classified. right? If you can have this kind of a decision surface. This is called a decision surface also, if you see some of the books. Okay. So can the perceptron be modeled to do this? Okay. So turns out that for this particular case where you have like a circular kind of decision surface, it can be adapted. So your original x was something like this. You had x1, x2 in 2 dimensions. Now, if you use your phi x as x1, x2, x1 square, x2 square, and x1, x2, right? So now essentially what are we doing? We're trying to get these weights, right? So w1 x1 plus w2 x2 plus w1 I mean w3 x1 square plus w4 x2 square plus w5 x1 x2, and if you have a bias term you have a w6. Okay, so that would mean a 1 here also. So what you're trying to learn is whether this is greater than 0 for the plus 1 class, or vice versa, right? Whether this is greater than 0 for the negative class. That's also something. I mean, nothing changes when you flip these inequalities, right, in your model itself. Okay, so here, this is a circle, so there are some settings, right, where there will be some w3 and w4 and w6 where this is true, right? So in that sense, you can enhance the perceptron, you can enhance this model, but more generally, this it has its limitations. I mean, if your function has this very nice structure like this, then you can do something like this. You can identify that, but otherwise, you don't know. I mean, so there are some limitations to the perceptron. Okay, is this part clear? What we did in this example when we moved it to a higher dimension. Um,
Ma'am, when moving to a higher dimension, how do we decide like what to take? Because here we took squares, but maybe the function to fit was a cubic or something different. So how did we decide?
yeah, so there is really no answer to that, like a fixed way to determine what your phi should be, right? So people, what they do is they try out different things. So if your data is like very small, like 2 dimensional or something, that, or even like, yeah, if it's 2 dimensional and you can visualize things, then it's okay. But in the moment you go beyond 3 dimensions, it's very difficult, right, to see what kind of function you want, how the configuration or how the geometry would be. So yeah, so there is no fixed answer to that. So what people do is they try out different kind of functions. So this is like a polynomial function. Sometimes they try out different kinds of functions. Okay, so these are actually called kernels. Okay, so more generally these are called kernels. So they try out different kind of kernels and see which one works. So that's as best as you can do. So that's kind of a limitation of working with higher dimensional data sets. Like even anything more than 3 also becomes hard, right? You don't know what to do. Okay, so in that sense, there's a lot of engineering component here where people have to try different kind of models or different kind of functions. So this is also actually a part of the modeling, right? What kind of phi should you use? What learning algorithm itself should we use, right? Or what overall, that's the idea. What model you use? So that that's why people try out different kind of things and then see what works best. And that's why there's a test data also. So sometimes you might learn everything well on the training set, and to the extent that it's kind of like a memorizing on the training set, but it does badly on the test data, right? So that's why you have to try your models on the test data, see the performance, and then choose what you want to go with. Okay, Advait?
Yes, ma'am, it's clear.
Yeah. All right. So, any other questions? So, Divyansh, you mentioned about hyperparameters. Uh,
Yeah, I kind of answering his question. Like he was asking how to decide these things.
okay. All right. Is it clear, Divyansh?
Yes, yes, yeah.
Okay. All right.
Excuse me, ma'am. Ma'am, what is
Yes.
the clear-cut meaning of the hyperparameter? Means it is a weighted or something else?
So hyperparameter is
Or it's
basically,
as you mentioned that x1 is square, x2 is square means these are the hyperparameter.
yeah, so let me tell you what a hyperparameter is first, because that's not something we introduced here, right? So there may be people who are not familiar with what a hyperparameter is. So a hyperparameter is anything that, you kind of tune, like something extra which is given to you, which the model assumes in some sense. Okay, so, and that's what a hyperparameter is. So here, so here the phis is, I mean, I wouldn't call it exactly a hyperparameter, but this is like a function that you use. What kind of, it's an intermediate stage, an intermediate function that you're going to use. Now, this is not something that's part of your learning. This is something that you assume beforehand. And you try to use this phi. I mean, that is a fixed function. Okay. So that is, so I think there's a slight difference between the terminology where hyperparameter is used. For example, where have you seen hyperparameters? So maybe we'll see something like in the next few classes, there'll be some other parameters which you have to assume. Okay, you cannot take it that, that is, you cannot tune that too much. I mean, you cannot learn that. That's what I mean to say.
And
So
the
those are
decay
the
constant
hyperparameters.
was the hyperparameter.
Which one?
The decay constant in learning, Q-learning and other models, which we have done till yet. That was
So
a hyperparameter.
which constant are you telling about? Can you just say that again?
In which decaying constant, in which the past
Yeah, the discount, right? The gamma
yeah
parameter.
yeah the
Yeah, yeah.
discount.
Yeah. So yeah, exactly. So that is a hyperparameter, right? So that
Ma'am,
is
but
some.
here we don't have any constant. No? We
Yeah.
have
So
the
yeah, so here that is not there, right? I mean, it's not exactly a hyperparameter in that sense. So I think what Divyansh means is that there is some function, there is some underlying function, and that's some assumption you have to make, and you have to try out different values, I mean, different kind of functions. So in that sense, I think that's what he means when he says hyperparameters.
So
So
like here we
even
are
in
assuming it will be in the nature of x1, x2, which we have decided, which are deciding. So that's also a hyperparameter. Even the selection of the model which we are doing is also a hyperparameter.
Yeah, so there is some difference in the way people refer to hyperparameters. The model itself, they don't usually refer to as hyperparameters, but usually there, some constants or some, very fixed parameters which are there in the model that they usually refer to as hyperparameters. Okay, so like Divyan said, the MDPs, right? There you had this gamma in Q learning, you had this gamma, the discount parameters. That is a hyperparameter. Okay, so here and this is some kind of a parameter for the model, like what kind of phis to use or what kind of kernels. Okay, so this is something that you can explore with. Okay, you can try out different values of these phis or different functions basically. Okay, Rishabh,
yes, ma'am.
was this your question or you had some other question?
No, ma'am. Actually, only I want to know that here what hyperparameter we are considering. So as you now told that we are taking the different type of like the firstly we will check for the squares of the data points or cubic of the data point, then it's behave as an hyperparameter. Okay.
Yeah. So yeah, so basically these things are tunable to some sense. Okay, you have to explore and see what works best. Now, something for you to just try out as a homework. Try to fit some Boolean functions. Okay, so consider cases. I mean, this is not to implement the perceptron algorithm as such, but suppose you have a Boolean function. So something like, you've seen in logic, right? Like you have x and y, right? So if you have x and y are Boolean values, then you have this operator and of x and y. Okay, so if I'm going to write this as my new function f of x, okay, so can you write this as a perceptron? I mean, is there a, can this be represented? So here what happens is, depending on x and y, let me call it x1 and x2 just to avoid confusions. So x1 and x2, so two features are there, and these are all binary. Okay, so maybe 0001, 1 0 1 1. So x1 and x2. So this is like 0 0 0 1. Okay. So okay, so take these as the class labels. So maybe these are like -1 and this is like +1. Okay. Try to think of whether you can write this function. Okay, so this is like the class labels. So if you have just this data set of these 4 points, is there going to be a hyperplane which separates these points? Okay, so can you find the correct W1? So what you need is W1 x1 plus W2 x2 plus W naught. Okay, so this is like the bias, or that was like the B's, right, that we had earlier. So this is greater than or equal to 0 for this point. And for these 3 points, we have W1 x1 plus W2 x2 plus W naught is less than 0. So can you find uh, W1, I mean, there's three numbers, W1, W2, and W naught, such that this holds. Okay, so just try this out as an exercise, so that then you will see, how to, visualize these examples, and it's just 4 data points. Okay, so just try to see this. So similarly, just try the other Boolean functions also, like and, or, okay, and maybe not is just one dimensional, right? So I mean, just try that. So that would be just one feature, and maybe something like this XOR also. Okay, just try to see if you can cast this using perceptron. Okay. So is the question clear, like what I'm asking you to try out?
Yes, ma'am.
Right, okay, so just try this out as an exercise. Now I'll just tell you one thing for like we saw that yeah, not all data points are, I mean, not all data sets are linearly separable. You can have things like this, right? So you can have like mostly they are separable, but maybe you have a negative instance here, maybe something here. So in this case, the perceptron algorithm is not going to work, and we need to build something further on this. So that's going to be our next topic, so which is neural networks. Okay, so neural networks are now like very popular. It's like the foundation for deep learning. Okay, and it actually builds on perceptron. Okay, so it builds on perceptron. So that's why we did the perceptron algorithm. So in fact, the perceptron algorithm is quite old. It's an old model, something like 1960s. That's when it came up. But what happened is, when neural networks came, it got I mean, neural networks became very popular, and today, deep learning is like so popular. So neural network is just a multi-layered perceptron. Okay, so I'll just I mean, maybe I'll just take 1 minute more. So what we can do is, this perceptron, there's a way to visualize this as a unit. So if I draw it graphically, what happens is there are these x1s up to xd, and there are these weights which are getting multiplied. Okay, so w1 up to wd. Okay, and there is an intermediate unit that's created. So this is wixi. Okay, and then what we are doing is we are doing some kind of a thresholding, right? So then we are doing something like this. Okay, so it's so then we are doing a thresholding. Okay, so what we did is, we constructed a function like this. So if your wixi, so summation wixi you take here, if it is greater than 0, we are saying that, it's a +1. And if it is less than 0, we are calling it a -1. So this is on this axis, you have the summation wixi, a single number. If it's greater than 0, it's +1, and less than 0, it's -1. Okay, so this is what exactly a perceptron is doing. Now, so this can be like one unit. Now, if you combine many such units, that is what is going to give you a neural network. Okay, so we'll resume from this point in tomorrow's class. Okay, so I'll stop here, and maybe I'll hang back if there are any questions. If not, thanks everyone.